Hi, my name's Greg. As I said last time, I'm going to try and show to you some examples of molar volume in terms of calculations. So let's start. Question 1. A chemist has a small flask with a 4.48 decimeters cubed of chlorine gas in it. Calculate the moles of chlorine present if the gas is under normal conditions or the gas is at room temperature instead, and I'll show you the small difference. So we know our equation, and we should always write this down first. N is equal to, so the number of moles is equal to the volume V divided by the molar volume Vm, okay? And we know that for part A, Vm can be assumed to be 22.4 decimeters cubed per mole. So we can put our 4.48 decimeters cubed divided by the 22.4 decimeters cubed per mole. And as you might notice, the units of decimeters cubed will cancel, and you'll just end up with moles. So you're going to end up getting 0.2 mole. Okay. Now for part B, there is a slight change, right? If a gas is at room temperature rather than just being at normal conditions, its molar volume Vm is actually assumed to be, and this is kind of more common maybe, 24 decimeters cubed per mole. Okay, so our value of N would actually change slightly because we'd actually have a slightly different number of moles. So we'd have still the same volume, but because our molar volume is slightly changed, we'd have 4.48 decimeters cubed divided by 24 decimeters cubed per mole, which would actually result in 0.186 mole. Actually, if I round, because it's 6 recurring, if we round, that gets you 7 mole. I'm going to round to 3 decimal places here, and that's our two answers. So a very simple calculation. Let's try and maybe do something slightly more difficult. So question 2, we're told that 60.54 grams of neon gas were used to create a neon light. Let's calculate the volume of neon used if it was, again, at normal conditions or at room temperature. So there's one thing we can calculate for both of these parts without having to do it separately 2 times. So we know, I think I selected the wrong tool there. Didn't really mean to do that. So if we say that N, which is the number of moles, is equal to mass M divided by the MR or the AR, and in this example it's going to be the AR of substance, we can say that N must be equal to the mass of neon, which is 60.54 grams, and I'm going to read of the AR of neon off the periodic table as 20.18. 20.18, and again the units, just like for MR, grams per mole. Okay, and we're going to get a number of moles of 3, so we're going to get 3 moles. Why is it moles? Because the grams cancel, moles, sorry, per mole, because it's on the bottom of the fraction, just becomes mole. So you've got 3 moles, right? Let's calculate the volume of neon at normal conditions. So if we know N equals V over Vm, then we can rearrange that to get N times Vm. So the number of moles times the molar volume gives us a volume, and hence we can say that the number of moles 3 moles, times by the molar volume, which, as we know, at normal conditions, is 22.4 decimeters cubed per mole. The moles will cancel because we've got mole and per mole, and so our answer will come out just in terms of decimeters cubed, and I'll get the number real quick. So the number is 67.2. It's a bit big, 67.2 decimeters cubed, so that's quite it's a bit larger than I thought, actually. And then for part B, we want the same, but at room temperature, so we're going to still use our 3 moles calculated earlier on, times by, we're going to multiply by the 24 decimeters cubed per mole, because remember, at room temperature, it's not 22.4, it's 24 decimeters cubed per mole, and this actually gives us an answer of 72 decimeters cubed. So this is a nice way of showing that if you increase the temperature slightly, the gas occupies, a gas of the same mass or of the same number of moles occupies a slightly larger volume. I hope this helped.